Hey, discussion there. Let's start the session. So the first speaker is Aihong Tang. He will talk about proving spin dynamics and magnetic fields in heavy ion collisions. Please start. 25 plus 5. I will wave to you.
All right. Good morning, everyone. It's my great pleasure to have this opportunity to discuss with you the probing spin dynamics and the magnetic field in heavy ion collisions. I guess for this audience, I don't need to spend too much on the introduction, but just to set a stage, we know we have these two nuclei passing each other that produce, I don't know, it erased my symbol of the magnetic field and global angular momentum. Anyway, so you will produce enormous amount of magnetic field in the middle, and it will also deposit a significant amount of angular momentum, and that's the two topics that I will cover today. For the strong magnetic field, that's the second part of my talk, and then for the global angular momentum, because it's through spin orbital coupling, it will introduce the spin at the quark level, then it will propagate into hadron level. So that's the first part of my talk, the spin dynamics. In my talk, I will mostly focus on spin alignment, and for the polarization measurements, we look forward to see Sergei and Michael's talk. Now, the global spin alignment, we know the spin states of a vector Masson that can be described by a 3x3 spin density matrix. And the rho 00 corresponds to probability of finding a vector Masson in one of the spin states, one of the 0 states out of 3 possible spin states. So a deviation from 1/3 will indicate the system has a preference in some certain spin direction. So usually in experiment, we can measure it either through strong P wave decay or dilepton decay. The formalism for each of them is slightly different, because in dilepton decay, you decays into a spin. The daughter carries spin, but in this case, the daughter has a non-spin. So the formula is a little bit different, and for the spin alignment analysis, is more about to recover a shape of a daughter shape in the parameterized frame. So with the daughter shape in the parameterized frame is a ball. Basically, you're looking at this cosine theta star distribution. The cosine theta star is the daughter's angle with respect to the quantization axis in the rest frame. So if it's the daughter's shape is a ball, then it's 1/3. Then it could be a standing peanut or a donut shape. This is a star measurement of global spin alignment of 5 Masson, showing in the red stars and the K star. We see significant global spin alignment for 5 Masson, and within error bars, we see a little for K star. This result has been a surprise, because there's a bunch of theoretical papers trying to explain the large global spin alignment, because if you follow the conventional wisdom, and there's a bunch of conventional explanation which I highlighted in this box. For those explanations, they predict the magnitude if we plot it on the same plot is just like within this bar. It's very little. So seriously trying to explain, and then there are two groups they invoke the group of series. They involve the strong force field fluctuation, and once you do that, you can indeed fit the data points, and with the including of strong force fluctuation, and you can even extract some quantities related to the strong force fluctuation, and that can accumulate a large positive signal as seen in data. So we also extended the measurement to BES2 with BES2 data, and you see that the BES2 data points basically agree with BES1 results that corroborate our previous study. So for this same framework, the strong force field fluctuation, you can also predict the rapidity dependence. The idea is there's a particle moving relative to the medium, then there's an asymmetry in the fluctuation in the direction perpendicular and parallel to the moving direction. This will be more prominent in the forward direction. So if in the in direction, if the global spin alignment is less than 1/3, because the 3 direction has to add to 1, that cause the global spin alignment increase with rapidity. So this is a prediction. Actually, once we put our data points from the theory curve, we request it from the theorist. I would say it's done a reasonable job. It's not perfect because obviously you see some difference, but as a first attempt, I think they did capture the general feature of this increasing with rapidity. The right plot shows the similar measurement. This shows the D star plus measurement from Alice. They also have the measurement from in middle rapidity, close to middle rapidity, and at a slightly forward rapidity. You also see, in general, the forward rapidity, you have the rho 0 larger than that around the middle rapidity. So what do we learn from this? Well, the story starts with the hyperon global polarization, and Sergei will talk about that. Well, from there, initially we think that if you take the square of that, you would get a global spin alignment, but that's not the case. Then we soon realize that in rho 0 measurement, what we are measuring is square's mean. So square's mean doesn't in general doesn't equal to mean square. So we are actually measuring the fluctuation of something. And we do know that the heavy-ion collision environment is a violent environment. It's full of fluctuation of quark and gluon fields. Now we understand the global spin alignment measures local field fluctuation, while hyperon polarization measures the mean. For the fluctuation, that means what we are looking into is the spin-spin interaction. So on that topic, actually we can look back to see what other communities, it's not a really different communities, it's also high energy community, they are doing in terms of spin entanglement. This one shows the E plus E minus collision at the best 3 collaboration. And they have this, the fluctuation measurement, you do see there's a correlation, and they also decompose into, actually they only show 3, but they decompose all the spin density matrix, 9 elements. And then from there, you can fit those spin density measurements. Then you can, this is E plus E minus decay into J psi, and then, decay, produces J psi, and J psi decays into a cascade plus cascade minus. And then you can figure out the spin from cascade, spin interaction between cascade and cascade minus and cascade plus. From there, you can fit this spin density matrix. So you can fit this S wave and P wave phases, and that's just the interference between 2 decay modes. And you study the difference between the particles and the antiparticles, and that would be a high position test of CP symmetry, but because in this environment it's really, really clean. So we can move on to a little bit slightly complicated environment as a PP collisions. This is done by the LHC. What they did is they take the top quark decay into a bottom and a W subsequently decay into a lepton and a neutrino. And the neutrino will carry over the spin. In this case, they really are inferring the top quark spin. Because you even don't have a chance to hadronize, then you got the W and got the spin direction carried over by the lepton. So basically, they study this quantity. The phi angle is the lepton, the relative angle between two leptons boost back into the top quark's rest frame. If this quantity is less than 1/3, then you will see spin, what they call spin entanglement. Indeed, you see the significant signal in this mass region. That's a very nice study because this has never done before, and it indicate that there's a significant spin entanglement between top and anti-top quarks. Well, the star experiment carried on for this. Now we know quarks spin are entangled. Whether that entangled spin will survive through the hadronization, that's a different question. That's what a star is trying to address. So what star did is that where we took the lambda and the lambda bar, this is the typical hyperon polarization analysis. Then we studied the spin correlation between lambda and the lambda bar. This is in PP collisions. You see we have the two relative rapidity cars, but basically you see this point is for lambda bar system, and the other two cases are for the same sign system. You see there's an enhancement for the lambda bar. That indicates that indeed this S, because the spin of the lambda is mostly carried by the S quarks. That means the S and S bar, if they have the spin entanglement at the beginning, they do survive, and we do see that spin entanglement even at the hadron level. So move on to a more complicated system, the heavy ion collisions. This spin-spin correlation study can benefit a lot more, because now you have the medium effect. You can turn the question around to use this as a tool to probe the medium. This is a theoretical study showing that indeed you can use that to study the vortical structure. They have so you have this local vorticity, and around this vicinity of a local vorticity that will introduce the spin-spin correlation between hyperons. They did a study of this, and you see they do this is theoretical calculation. You see some structure, and you see some relative enhancement at a small angle. Well, there's another mechanism that which I talked about. That's carried over from the global spin alignment, which was induced by strong force fluctuation. The idea is this strong force fluctuation is mostly due to the phi meson field, and if this strong force has leakage outside of the hadron, then you would still see some spin-spin correlation between hyperons. Indeed, for this, you have to do a spin correlation, and you need to extract all the 9 components of those spin-spin interaction. This is becomes a very hot topic, and currently in STAR, we actually have multiple groups working on this. So to recap, for this spin-spin correlation, in my opinion, it opens a new dimension to allow us to study a lot of things. In E+, E- collisions, you could use that to study some fancy clean CP test. And then from PP collisions, we know that from Atlas experiment, we know that quark spin are entangled, and from STAR, we know that that entanglement would survive the hadronization. For PA system, I haven't seen any studies on that, but I could imagine somewhat medium effects. And for the heavy ion collisions, well, that because of the medium effect, we would see that can use that to either probe the vorticity or strong force. Well, we'll see. I will make another note on the global spin alignment. That's and also its relation to the current magnetic effect. Indeed, this rho 00, you can imagine the rho 00 in particularly rho 00 for rho meson, which decay into pi plus, pi minus. That's the bulk particles in heavy ion collisions. the rho 00 is like V2 in the rest frame. We know that the V2 would have an effect on the delta gamma, and indeed rho 00 also have a significant effect on delta gamma as well. As this plot shows, the rho 00 increases increases with delta gamma, and also rho 1 minus 1, the real part of rho minus 1 decreases. So the story is rather complicated. So far, we do not have any experimental efforts trying to pin down what exactly the influence is. So the second part of my talk is about the electromagnetic field. I needless to say that this is an important topic, as the EM field serves as a central hub to many other interesting physics phenomena like the CME and the Breit-Wiener process and the elliptic flow splitting or fine structure on phase diagram. And this has been, we have been talking about for a long time, well, for almost 20 years. So it's usually expect that we would expect a strong magnetic field, but we haven't seen very solid evidence yet until recently. So this is a paper by Starr, basically study vacuum birefringence in the vacuum. That's actually probing the strong initial magnetic field at the very beginning, because this is in very peripheral collisions. There's no medium yet. For what has mattered to CME and other physics phenomena, what you want to know is the magnetic field in the medium. So in this part, that has been a big question. So this plot shows the lambda and lambda bar polarization. We were hoping that we can see some difference. Then we realized that the magnetic field at the time when the lambda and the lambda bar, the hadronization time is already probably very weak. This plot shows that the difference shows within error bar, it basically is consistent with 0, or maybe you can say consistent with anything. Let me decompose this EM field. It has a few ingredients before I move on. So it has a Hall effect, that's the initial Lorentz force. And then it has a Faraday induction that basically acts against the initial Lorentz force because there's a medium response to it, plus Coulomb effect. Those two effects acting against each other. This Hall effect, say, twist the particle to one direction, then the Faraday and Faraday induction and the Coulomb effect push the particle to the different direction. And we have to keep in mind the Hall effect is more relevant for heavy quarks at the early stages, so it's more relevant for the D0 V1 splitting. The calculation indicates that the calculations indicated the Faraday plus Coulomb effect dominates over Hall effect for light hadrons. So we have to, before we move I show you the data, we have to talk about a little bit about another bigger component, that is transported quarks. For the proton and the antiproton, because the proton has UUD, so it has 3 quarks that are transported quark candidates. And for the simplicity, I will just say they are transported quarks. I really mean transported quark candidates. All right, so that means the proton is more influenced by transported quarks than antiproton. That means if we think transported quarks carries a positive V1, then that means this gives a positive contribution over the V1 difference if you take the difference between proton and antiproton. For K+, it has only 1 transported quarks. So you would also see that it has a positive contribution, but its contribution will be somewhat less than proton and antiproton because it is 1 versus 3. For pions, the story is a little bit subtly complicated because both pi plus and pi minus has a transported quark, but because we are talking about gold-gold collisions, gold-gold nuclei is neutron rich. That means pi minus are affected more than pi plus slightly than in terms of transported quark effect. That will give you actually negative contribution as opposed to the case of protons and kaons. And for pions, this effect is really the second order because you are talking about the difference between two transported quark. There you are talking about 1 versus 3. That's a different order of magnitude. This is the cartoon to assist you to digest the data that I will show later. So for the transport quark effect, this is a function of centrality. You would expect is more or less positive contribution. This is a line which the intuitive thinking is also verified by various models. Then for the EM field effect, it will drag this thing down. So if you add these two effects together, you will see in central collisions, the transporter quarks dominate the effect. Then in peripheral collisions, the EM field dominates the effect. And then there's a sign change in the middle. So also from this decomposition, you will see the effect will be biggest for proton and less for kaons, and probably a little for pions. And oops, sorry about that. So this is what the data shows. Yes, we need to add some vorticity into that. Anyway, this is the proton. This is the kaon. The blue points are pions. Indeed, you see in central collisions, the transport quark dominate and in the peripheral collisions, we see the EM effect drag is down, and there's a sign change. You also see we have this measurement for 200 JeV, gold, and ISO bar. We also have 27 JeV. Actually, the effect in 27 JeV is even bigger. Here is scaled down in order to put that on the same slide. So that all the features qualitatively agree with this two-component competition mechanism, and they indeed, this hierarchy will also agree. So I hope we can take this, and this data point can provide more constraint as we discuss going on. And for now, I think this electrical conductivity of QGP used in this particular model, this only has the EM field effect. It lies within a possible interval. We cannot claim that we have very accurate constraint, but at least the eyeballing it, I think is given a reasonable measurement. So again, this as a initial attempt, I think it is not a bad job for theorists. Oops. I don't know what happened, but I can explain to you on this slide. I don't know whether they downgrade the resolution. You look okay on my screen. So anyway, so we have this measurement for pion, kaon, proton. That's what I showed. Now we also added in the lambda. So that's an interesting feature. I will show you that for proton, you have 3 transported quark. Lambda, you have 2. Kaon, you have 1. For pion, I would say you have negative because acting in the pi minus instead of pi plus, instead of the positive particles as opposed to other 3. So if you look at this transported quark contribution, you will see indeed even for the 3 transport quark case, you have the most contribution. Then you have a 2 transport quark for lambda, it's slightly less than this one. Then it becomes less, and for pion it almost disappeared. That again, this is telling us what is at work is the quark level contribution, because it's really governed by quark level contribution for transported quarks and also for the EM field effect. With that, well, I think this we also can cross-check the lambda with some combinations of quark. So basically, you take the proton and the antiproton and kaon combination. This will give you the same configuration of the quark contents. And then you take their V1 and you plotted the lambda particles versus this combination. You see they agree with each other very well. So what we learned that lambda, as many people were saying, lambda is a neutral particle, you should check that, and you would not see any splitting. That's not true, because the lambda is neutral indeed, but the magnetic field at that time is almost gone. What matters is really the quark level contribution. So lambda also being neutral is not special in this case. It has to obey the same rule other particles obey. Previously I showed this effect is more significant in lower energy, and this is in agreement with many theoretical calculations. Dima also showed some versions in his talk. Here I show another version, and the reason I show this version is they specifically calculate the magnetic field at the freeze out, because what I showed are V1 from mostly light quarks, and for light quarks they do not retain the memory from the beginning. What they care is only the moment that they get hadronized. So what matters is the magnetic field right at the hadronization surface, because they can be pushed around very easily. Any initial effect they got lost, but they remember the last moment. We also studied the system size dependence. We do see we have a uranium and gold. We see the uranium is larger, and this dashed line is a calculation in hydro with the inclusion of both transported quark and the EM field effect. And indeed, the dashed line is without the EM field effect. Once you include the EM field effect, you see that brings the very good agreement. So these are some ingredients from this model. Indeed, they can predict the general future. So I left some takeaways for you to read.
Okay, let's thank Aihong for the very nice talk. And Giorgio?
Can you show the physics explanations for the spin alignment that you had sort of the table? Just to say, there is one missing. Our paper published last week, and the thesis, this one, which we defended 3 days ago.
I see, I wasn't.
The point is, no, this quark coalescence, I mean, presumably was done in, the table.
This one?
I mean, in hydrodynamics, by causality, this was talked about in other talks, spin and vorticity are not necessarily in equilibrium. And if you have coalescence within a vortex, then spin alignment and baryon polarization could basically be very different from a Cooper-Frey prescription. And this is enough to, you can describe, I mean, this is not falsifiable because we have a lot more parameters.
Okay, I see.
However, if you measure, I mean, you have these diagonal matrix elements, but as you say, it's a 3x3 matrix. And at least in J-psi and maybe in phi, you can measure the off-diagonal matrix elements as well. You know, the rho 1 minus 1, exactly. Cooper-Frey, I mean, you know, statistical mechanics predicts a maximally mixed state. If you start seeing non-trivial dependence with the theta angle for off-diagonal matrix elements, that's sort of a smoking gun, that it's not just statistical mechanics, it's coalescence or something like that. It's at least partially an open quantum system. So this is a possible explanation. It's not, with 5 parameters you can fit an elephant, but we have a signature,
Okay, thank you for the comment. I will read in paper, but on this off-diagonal term, actually, we are thinking of measuring that, but not yet for just psi, because just psi is more challenging for us. Well, we're actually thinking of measuring that for phi first, and we'll see. Yeah.
Right. Thank you. Last question by Sergei. Quick, please.
I have two short questions for the spin alignment also. You mentioned on one of the slides the strong force fluctuations that predict this positive delta rho 0, 0.
Yeah.
But at different centralities and different PT, you know, you do measure it's negative. So it means it doesn't describe the entire data, right? And this is first question. And the second question is about this rapidity dependence. Are you sure it is applicable? Because all the calculations are done in this for static medium. And your or your, say, phi produced at rapidity 1 definitely is not produced from static medium. Can you comment on that?
Well, yeah, this is really a question to a theorist. For your first point, I don't know, but I would see from their calculation, they also shown this comparison of the strong force field fluctuation as a function of PT, at least from what they claim, they show that there's in general agreement, but I don't know the ingredients. For the second one, I think their major point is that you have a suppression of fluctuation in the direction of traveling, the relative direction of the particle moving in the medium. So you got a suppression in that direction. So for that direction, you got a rho 0, 0 less than 1/3. But now you have a rho 0, 0 in x, y, z direction has to sum up to 1. So that means when you study rho 0, 0 in y direction is is greater than 1/3. I don't know what else I can say. Yeah.
All right. Thank you very much, Aihong. Let's thank the speaker again. And the next talk is by Sergei Voloshin.
Other side.
All right. He will talk about polarization in relativistic nuclear collision, about the recent measurement and open questions. Please go ahead. 25 minutes.
Okay, thank you. And I thank the organizers for inviting me to give this talk on recent results related to the polarization measurements in heavy ion collisions, which I understood as what happened from the last conference. But for that, for 1 year. But for that, I have also just to show some old results and introduce why those new measurements are done and what is the reason for them. And so this coordinate system was already introduced, and so the x component is along the impact parameter vector, and z is the beam directions, and so that explains when I write this py or pz, and that's the main topics, and this in like an dark, I don't think I will be able just to go there due to the time. What happened during this last year that our review with Takafumi was published. And so in this review, there are many reviews on polarization, but what we tried just to keep the physics on accessible to graduate students level, almost on qualitative, but we did pay attention to the technical details, and you can see that it is only a small part of the discussion of the real results, but quite a lot of introduction to physics and also to the measurement itself. Just to put it in the overall perspective, so I just, when it started more than 20 years ago, and my personal interest in this was just what related to the spin alignment, and namely if, for example, vector mesons are polarized and decay, that would contribute to elliptic flow, and this is 2004 was the year when it was actively discussed the reason of the large elliptic flow was done. Initial prediction was very large, and so that's contributed to this worry, about 30%. And then in 2007, we developed a method how just to measure, and it was measured. We measured it is definitely less than 2%. And then it just, the story continues. And for example, this paper by Barbara Miklos and Georgia, it really probably was the first time it was used. Vorticity, I haven't checked, but it might be the first time used in the relation to the heavy ion collisions and local vorticity. But the real breakthrough was done by Francesca Beccattini, which I learned from a coffee break. He stopped and just said, oh, he was able just to do it, calculated in assuming statistical equilibrium. And I didn't already go to the details, I didn't hear, but just wrote that you assume statistical equilibrium, solved many things. And that was done. I really measured it at low energies, analysis led by Mike Lisa and his student. The next real stop in terms of the understanding and development was this quark matter SQM in Utrecht, where many things were understood in terms of the contribution to polarization of elliptic flow and many other stuff. And so the measurement was done, and just a separate issue which I show also new results, and the polarization of sigma, of psi and omega, which is also important in order to understand just the entire, that it is a global phenomenon. And I don't take a spin alignment, also I might have some comments. Anyway, so this is just the original from a lot of discussion, in fact, over here. But for me, it's just indeed a very important thing that non-relativistic limit, and this limit, as Boltzmann can be derived now, probably with some hint even undergraduate students, just few lines of derivations of the, if you assume a statistical equilibrium of angular momentum. And that really sets the scale for many, at least estimates, because, for example, you remember that the lambda has a mass of 1 GeV and temperature about 100 MeV. It's all non-relativistic, in fact. And so this is already some of new results and old results, but you did see a different plots before on energy dependence, but here is in a different way. This is like an only 300 GeV, but it's scaled by a factor of 10, and you compare with other things as a function of centrality. What is on the right is shown, it's a new measurement just submitted recently for isobar, and also isobar compared to gold. That's one thing what we do. It is goes along with some theoretical predictions. I don't hear the authors, but I believe it's from Chun Chen and his students. And the data in general agree, but that's one thing of study. Another thing which Aihong already mentioned is about trying to extract the magnetic field. And this is the previous measurement done before, led again by Mike Lisa. I realized that also just to take this data and analysis. And so if I take this difference between lambda and just like a back on an envelope estimate of the magnetic field of this delta P versus CB, you can put it theoretically for 200 GeV, but just to give you an idea what you can get from such measurement is just the upper limit on the magnetic field. But what happened after that, and Aihong also already showed one of the slides, and this is a beam energy scan. This is a new measurement and start preliminary. What is on top, on the left, it is just submitted in the same paper which I already mentioned from isobar, and so you can see that it is the difference between lambda and anti-lambda polarization basically agrees with 0, but and in terms of the upper limit, you wouldn't go probably as a different, but anyway. Another thing is that what happened at SQM. We understood even some calculations. In fact, the story of this plot is quite interesting because it was calculated in 2015, but the authors couldn't understand what the results, and it wasn't even it was even excluded from the publication. And then with Francesca, we discussed many things at Cork Meta in Chicago, but at SQM, with all discussion with Francesca and other people, in fact, from Dubna also. I just showed at SQM some simple calculations. It's real. It's not even just a Monte Carlo from a so-called blast wave when you parameterize the velocity field, and you can calculate what is the polarization. Even if you took these calculations and what was presented or later published by Francesca and Karpenka, You can see if you compare the numbers, like a 1% maximum here, and you could see that what blast wave predicts is at least order of magnitude smaller. That already was quite interesting. But this is just as a measurement which many of you know. The star measured the first measurement of the things. And indeed, these hydro calculations showed, again, first of all, it is negative sign, and it is scaled by factor of 5, so it's just completely off scale. And the blast wave, on the other hand, if you took some parameters of the blast wave, there are some uncertainty on that, but this is on like a brownish curve. This is the parameter which no modification, you just plug it from the parameters measured in 2005. You take star paper, take parameter, put it in, and it goes over the data. But you had to understand the hydra, and most of you know the story, but just for everybody. So one of the contributions which was developed during those years is the so-called shear contribution from a symmetric tensor. It is important just to realize that there are these two momenta. All those equations are, by the way, I just took it in the rest frame of the fluid cell. And so these are would be non-relativistic momenta, and that is important because it should be really suppressed. But in general, they claim there could be some explanation coming from this so-called shear-induced correlations. After that, we did some measurement also with ALICE and LHC, and again, now you can see two contribution, and just to explain what is S quark or lambda quark, this is shear-induced contribution, but as I mentioned before, sorry, I should, as it doesn't go, it's below. As I explained before, there is this contribution to momenta, and so for quark it is definitely really it's velocity state P over E, and so for quarks is a larger contribution, and for lambda is a smaller. That's the difference why it is. But this is a comparison, and so what I wanted to show what is new in this direction, so we just try to increase the statistic, and this is really new from ALICE, from run 3, and you can compare the error bars shrink probably factor of 3 or so, and so the story we are going to study more and more details in these directions. Another new measurement related to that is this isobar measurement, which was published a year ago or so. And we do compare with different contribution, but I think the real explanation is still coming. On the last, in Timisoara, on the last meeting in Timisoara, it was presented really as discussed. Now it's submitted for publication from CMS, and it also added as a contribution from this different theoretical curve. You can see it's kind of qualitatively agree what it is in heavy ion collisions, and it's very far off from any theoretical calculations. The same thing is happening also at beam energy scan, so we do measure this stuff and try to compare. Also, this with anti-lambda measurements become very uncertain because it's not that many anti-lambda, but nevertheless it is measured, so just again to flash, and it also compared also to the shear-induced polarization, but at low energies has become important also such things depending on the chemical potential, which is large, and one thing is so-called spin Hall effect. And that's, again, I'm just flashing other things. You can see that we did measurement with this PZ, and it was kind of the shear-induced gave something positive. On the other hand, not fully contribution, not fully explaining the data, and we wanted to look at the different measurements which would be still sensitive to shear-induced polarization. And this is one of them is phi dependence of this PY. So it's not a global in terms, because it's now depends on locally. And so as there is this contribution, in the first calculation did show that only with including in shear, it is kind of would agree with the star preliminary data. But what I wanted just to say is that in principle, such dependence that it's a larger PY or polarization for particle going out of plane goes with very simple calculations. If you just do and calculate similar to the blast wave, what is dV, dx, and calculate the calculations. And so what is shown on the right, that I just simply calculated using this participant nucleons, and on the bottom is just exactly this contribution, which would contribute to y component of the polarization, and you could see this red lines, so the particles which are pushed in plane should be enhanced. And so for me it's very difficult would be to separate from other things. Really these calculations already, just in fact preparing for this talk, I just found that what I did is very similar, and that could probably explain to other people what Georgia and collaborators used more than 15 years ago, which would correspond to fire streak. So I just counted number of participants from different things, and that gave me the velocity, and from different nuclei gave me the velocity, and that I calculated. And so this is similar things, also the different calculations, but I would just better go further. And so just to say that it was measured, this PY, and we put some curves, the star puts some curves on this. It's not resolved, and I think again the qualitatively in the very simple consideration that what we observe we would see. This I discussed already and had even the slide very similar, and so the shear-induced polarization is very strong contribution is from dVz/dx, so the same thing which was giving global polarization. But it wouldn't be if you go to the higher harmonics, and so that's I think what I propose is we should go to the higher harmonics. Also I proposed even before Shearer was mentioning, so it should be because and even this plot from this my Utrecht talk, it just includes this n. So for any harmonics, we should observe this modulation for this z component, and that was measured and published again just recently, but it was discussed last year from ISABAR, which is very good data. Again, we compare it with the different models. It's kind of semi-qualitatively you could explain, but that was measured. So I'm presenting just the data. That's one of the measurement, and then it was measured also the PT dependence of the third harmonic and second harmonic comparison. They are not different. I mentioned the fourth harmonic. I removed plot because it wasn't published. Also, it was measured just for technical result, technical reasons. It was not published yet. But what is new, and this is really very nice, and indeed very new. And in fact, if I think it was just the first shown just only a few days ago. So Alice measured it also with this high statistic measured the third harmonic, PZ, and that is a comparison on the bottom of the second harmonic and the third harmonic measurement from Alice. Now I'm come to another thing which I also think were quite interesting, and the measurement of Xi and omega. And it was already mentioned in somebody's plot, or it was discussed how yeah, it doesn't show. So this alpha parameter, in fact, is very important to measurement because it gives you asymmetry, and the symmetry is measured to measure the polarization. But if you look on this table, you see that for omega, this asymmetry is less than 2%, and which makes unpractical this measurement. But it is interesting that when the hyperon decays, it transfers some of the polarization to daughters, to the hyperon daughters. And there is this equations which was derived by T.D. Lee and Young long ago, general equations of the polarization of the daughter in the daughter rest frame from the polarized parent. And it has three parameters. All those three parameters are alpha squared plus beta squared plus gamma squared equals 1. Parameter alpha describes as violations of parity, and beta violation of CP. It just happened that it was only one parameter alpha measured for omega, and this is alpha, which is very small. You can assume for CP, beta should be even smaller, which left for gamma only plus minus 1. But it was not measured, and the people created the entire experiments to measure this stuff. What I'm saying that if you assume that omega would be also globally polarized, then from measuring this one and this line, this transfer of the polarization to lambda depends directly on this parameter. And if it is plus 1, it would be just 5 over 5, so it's just the same. But it would be negative even if gamma equals minus 1. And so that's interesting by itself, and that was also measurement which we did with Takafumi that was published. And so this is omega. It kind of favors of this plus 1, but you can see the uncertainty. Yeah, 5 minutes, fine. The uncertainty quite large. And by the way, it is also important that you expect, because the spin of lambda is, or spin of omega is 3/2, you expect larger polarizations in lambda. But that was all the introduction. This is just a new measurement, still preliminary from STAR on Xi and omega. And so you could see that for the both for the Xi and omega, as at least for the on the left for Xi, you do see it's slightly higher than lambda, which might be related to the when it just froze out. But what is important related to what I was saying on the previous slides is that this omega was measured polarization, and it does look that it is okay. We have more confirmation that it is positive, which means very important also measurement of this gamma parameter for the omega. And so another thing, again, very new from Alice, they also measured this Xi. In this case is the Z component. It's very difficult to measure in Alice the Y component because we need the first order reaction plane. But this is the first measurement of Xi in Z direction, of Z component of the polarization, which is really great, and it does agree with the lambda as more or less expected. Just a few, couple of minutes, I just only mentioned that I was mentioning different contributions, and for example, the shear contribution from the even such contribution as the spin Hall effect, and there are similar also from what is on top from acceleration or temperature gradient. Also, we didn't discuss, so there were no any presentation real on the calculations of this stuff. I should say I still don't understand some of the calculations, because I do expect that all those, due to this kind of extra factor of P in front of either acceleration or temperature gradient or shear, I would expect them small, but It's not. Yeah, and one thing also which was done on real on SQM, and I have from my some proceedings, there's another things we were discussing, in fact, was also kind of triggered by Giorgio's idea of the jets. And so what I discussed is the copper-gold collisions, and in fact, we mentioned, but I didn't took it seriously, but Mike Lisa would be talking more about this stuff. And so, but I even just mentioned is for one thing is that it is a measurement quite difficult. Probably Mike definitely would go with that. But I also wanted to, it's not on the slide, but I wanted to mention that why the measurements are difficult, but the spin correlations, which Aihong briefly mentioned, should be possible to do, and we're also doing it in a different components that probably could be just measured. And this is the kind of the last slide for this stuff. And I wanted just to show, and yeah, I'm sorry, but we did have a presentation on this kind of what I saw, circular polarization, a phi component of the polarization in asymmetric collisions. And so using this model which I already just presented, I can calculate similar to what is on the right. I can calculate what would be in the copper gold, but to understand the slide, I took this psi reaction play equals 0, that's why it's slightly shifted. But comparing the magnitude, which is weighted with the number of participants, which is, gives you idea how many lambda produced, I would also agree with the previous speakers that it is of the same order, and so it should be measurable. And for that, yeah, okay. I have very generic conclusions, so there is no need probably for even to read it. So I'm just open for questions.
Right, thank you very much, Sergei, for the nice talk. So the floor is open for questions.
Can you show the omega? This was a bit, for me, it was disappointing. I mean, not like, well, the omega, the one where you talk about the difficulties, that it's impractical. This was the disappointing part. So I have an experimental question, yes. Because at first I was like, I mean, in the last talk, the whole off-diagonal matrix elements. The omega spin density matrix has 24 matrix elements. And in principle, to a naive theorist who thinks that experiments are made of magic powder, they're all measurable because it's two sequential parity violating the case, you know. But now you say that it's actually even impractical to measure the omega polarization directly. So do we have any hope to see the omega off-diagonal matrix elements? Or it's impossible?
My guess it would be not possible, but yeah, I don't know exactly what would be the distributions and which parameter and which combination it would be entering in there. This is what is on the top, is just a generic only for, yeah, 1/2. And it would be described by this parameter, which also would be applicable to omega. Okay, but I don't know if there could be more parameters for this 3/2.
All right. More questions? I have maybe one. So like at the slide 25, I think you showed the new data from Alice, I think it was, like for
20.
Yeah, exactly. So the upper panel there. So this PZN is in fact PZ as a function of n phi, right? So it's not the harmonic, right? I'm understanding correctly. Because then there is like I don't know. Usually like this notation for the harmonics. So this is just PZ.
N is just the harmonics, right? N is
it's
harmonics.
just PZ with, yeah, okay.
There is this Yeah, the notation, I did have on some of my slides, but I didn't probably explain. But for example, this notation, it just means that the amplitude of the sign component.
It's clear, it's clear. All right, thank you very much for the clarification. Okay, so if there are no other questions, let's thank Sergei again. And the last speaker of the morning is Fuqiang. All right. So let's welcome Fuqiang Wang, and he will talk about measurement of azimuthal correlations with spectator and participant planes to search of the chiral magnetic effect. Please, 25 plus 5.
Okay, yeah, long title. First of all, I want to thank Anna and Giorgio, who just left, and the organizing committee for the opportunity for me to present you some recent measurements from STAR on the search for the chiral magnetic effect. Well, this audience does not really need an introduction to the CME, but briefly, QCD predicts the existence of non-zero topological charge states, and those topological charge states, the Grouin field will induce chirality imbalance of the quarks, and if you put those quarks into a strong external magnetic field, you will have electric current or a charge suppression. So in the final state, and hopefully we could measure it. So clearly this is a very important physics, fundamentally important, and we think heavy ion collisions can, a good place to look for it. Now, if we don't find it, that does not necessarily mean that CME is not there or CME is a wrong physics. It's probably just mean that the effect may be too small to measure. But if we do measure it, if we do find it, that it could be very, very important, because that tells us, we have chiral symmetry restoration, local parity CP violation in the strong interaction, and it could have may be related to the matter-antimatter asymmetry of the universe or the strong CP problem. So here is kind of my outline. I don't know if it works here. Okay, so this works. Let me go back. So very briefly, the delta gamma observable that we use to look for the CME. Very brief discussion on the flow-induced background. The main meat of my talk is going to be on, maybe the wrong direction, on the non-flow contamination. How we estimate the non-flow contamination? Okay, yeah, but the laser pointer? Yeah. Oh, okay. Oh, okay, all right. I was pointing to the wrong direction. Yeah, so after that, we'll report some recent results from STAR after the removal of further non-flow contamination, and briefly summarize at the end. So the delta gamma observable, this was proposed 20 years ago, more than 20 years ago by Sergei Voloshin. Now everyone is using it. It's really a convenient observable. So what we're looking for is a difference between the two-particle azimuthal correlation with respect to the reaction plane, difference between the opposite charge signs and same charge signs pairs, and the delta gamma variable. This delta gamma variable should be positive if we have CME. Indeed, we did observe from the very beginning, very early results from STAR and then later Alice. We did observe very significant delta gamma charge suppression across the reaction plane. Now, the interpretation in terms of CME is difficult, and the difficulty is because of the large flow-induced background. This background is basically due to the coupling of the intrinsic two-particle correlations, like the low decays or jets, with the overall elliptic flow of those background contributing sources. Simply with some algebra, simple algebra, it is proportional to the overall V2 of the event. And it's inversely proportional to the multiplicity because the number of background sources is approximately proportional to the multiplicity. Okay. So one way to handle the background is to use isobar collisions, and that was also proposed initially by Sergei more than 10 years ago, 15 years ago. And you all know the results of isobar collisions. We expected the background, or we hoped the background to be the same between the two systems, but it turned out that the backgrounds are not identical due to subtle differences in the nuclear structure, which produce different sizes of the nuclei, and therefore slightly different energy densities, and therefore different multiplicities, which is relevant for the background. We can have, approximate rough estimate of baselines just using multiplicity scaling or the pair multiplicity scaling. And these are the two dashed lines, and you can see that the data points, which is the double ratio of ruthenium over zirconium of this delta gamma over V2, we expect this to be above 1 if we have CME, and actually we got something that is significantly below 1. But it's all these data points fall between the kind of the naive baselines. And clearly, we need to understand more. And recently started very careful work on estimating the further non-flow contamination. And the paper, 2 papers were published on that. And the final results are that the measurements are consistent with our refined background baseline estimate, including flow and non-flow. And so we could only extract an upper limit of 10% of CME in isobar collisions. Now, this does not necessarily mean that the CME would be also that small or 0 in heavier systems. And this is because the signal-to-noise ratio is much, much smaller in the smaller isobar collisions than Gorda-Gorda collisions. I would think more than factor of 2. And the reason being that the background is inversely proportional to multiplicity, so there's already a factor of 2 there. The magnetic field is slightly smaller in the smaller system. But more importantly, the decorrelation effect between the magnetic field direction and your harmonic direction is much, much stronger in the smaller system. This is a model study from Alice, actually for xenon and lead collisions in terms of the size, also about factor of 2, so that's relevant. And they see a decorrelation effect, or the net effect of the magnetic field times the decorrelation to be on the order of 10, or between 5 and 10. So maybe the signal-to-noise ratio is indeed factor of 10 smaller or more in the smaller system. So it's very hopeful that in the larger system, we will have a larger CME. So we go back to the Gorda-Gorda collisions. Okay, this is what was published 2-3 years ago already by Starr, and this is a method using 2 planes, spectator plane and participant plane. So the idea is very similar to isobar collisions. You make 2 measurements of delta gamma with respect to these 2 planes and then compare them. And this is actually nicer than isobar collisions because this is a single system. Everything should be the same. Not like the isobar collisions, there is subtle differences between the 2. This way, because the CME is more relevant for the spectator plane, it's perpendicular to the spectator plane, so therefore the delta gamma measurement with respect to SP is stronger for CME, and it will be weaker for the flow background because the flow is really along the participant plane. So by making these 2 measurements with different components or different fractions of the signal in the background. With simple algebra, you can extract both the signal and the background. And that's actually measured in STAR. And the blue points are the peripheral collisions and are kind of consistent with 0. The red points are from medium central collisions. And there is an indication of a positive, we call FCME observed. And this is after the flow background, flow-induced background is completely removed by design using this method. Okay. Now, as we know that from the isobar collisions, we know that non-flow contamination is actually very, very important. And we have to really understand it. Now, what is the non-flow contamination? Well, by using this cartoon. So this is the SP measurement. We use ZDC to measure the spectator plane. There's no non-flow because it's a spectator harmonic plane. The TPC measurement does contain non-flow. There are two parts of the non-flow. One is the simple V2 non-flow that we all know. This is because we measure delta gamma by dividing C3 by V2, and if your V2 is contaminated by non-flow, your delta gamma is affected by non-flow. These will tend to, and I don't know if it works, this will make the TPC measurement, apparent measurement, smaller because you are dividing by a bigger V2. And the difference between ZDC and TPC is the indication of the CME signal. And since your TPC is now artificially, quote unquote, smaller, you are getting a bigger FCME observed. Therefore, you need to correct for that. And that correction is negative. Now, the other component of non-flow is the genuine, should not say genuine, it's the reaction plane, I would like to say intrinsic three-particle correlation. It is really the reaction plane independent three-particle correlation, like the three particles from the same jet or from a dijet, okay? And this is included in the C3 measurement, right? So making the C3 bigger than you would like. So the difference is smaller, your FCME observed is too small compared to the truth. So you need to correct for that, and that correction is positive. So you have two corrections, and they kind of partial cancel each other, and that's a good thing to have. So by putting things together with a few steps of algebra, you get that the FCME is, and I really can point, here we go. So this, here we go, yeah, it's small. Yeah, this is the double ratio that we measure. The double ratio of ZDC measurement over TPC measurement of the delta gamma over V2. And this double ratio is really nice because actually all the resolution effects are canceled. So if you see something that is a lot larger than 1, you are there. But unfortunately, this is very close to 1. And the measurement is this. Divided by 1 over little a squared, and this is the little a is from the V2 ratio, and this would be the original FCME observed, we say, with only flow removal, but still containing non-flow. Now the non-flow contribution from the V2 non-flow, as I said, is negative. So it's simply subtract the non-flow fraction in V2. So it's -1 here. And of course, there are corrections onto this little a from the ratio of the two V2s, some corrections on the numerator here. So there's a prefactor that is modified as well. The three-particle non-flow contamination is in here. It is, and we'd like to express this in terms of this ratio, C3P over V2P. So C3P is the three-particle non-flow, and V2P is the two-particle non-flow. And this is the red epsilon NF V2 non-flow divided by V2 non-flow, that really the same thing. So this divided by V2 2P is really the real V2 square, right? So this whole term is really C3P divided by C3. It is the reaction plane independent 3-particle contamination over your measured 3-particle correlator. Rather straightforward. And this correction is a couple of percent, a few percent. And then there's prefactors. So with that, and I hope I explained the non-flow contamination clearly, the algebra have several steps, but I assure you that this is correct. We've spent more than 3 years on that, including the isobar collision data. So let me now tell you how we decompose the non-flow. So the V2 non-flow we decompose from data by fitting the 2-particle cumulant with flow plus non-flow, and the flow would be, we did measure flow, so we don't assume any dependence of flow on EDA and so forth. It's just a measurement. We include the fluctuations. We model the non-flow with Gaussians. So this is a fit. This is data, and the fit is the curve. The blue is the flow that you, the real flow that you get from fit, and everything else is non-flow. Okay, and this is the non-flow, flow, non-flow results for 4 event and sub-event. 4 event, we take all particles from the entire TPC, we do cumulants calculation. Sub-event, we divide the TPC into 2 halves. We take 1 particle from here, other particle from there, do 2-particle cumulant. For 3-particle cumulants, we take 2 particles of interest, the alpha beta particle from one side, the reference particle C from the other side, do cumulants. Okay, but here the right plot is the non-flow contamination in V2. In medium central collision, it's a few percent. 4 event is larger than sub-event in terms of non-flow contamination. It goes up in peripheral collisions, as we know. It goes up in central collisions, as we know, because central collisions, the flow is relatively smaller. Now, the 3-particle, right? Let's see if, okay. Okay. Yeah, but now it's not working here. Yeah, so this is the laser, that's good, but this is not working. Yeah, so you have to go up and then it will automatically work. All right. Okay. I guess the machine wants you to stare at this slide for a longer time to digest it. Okay, so the next slide, I will tell you 3-particle. Oh, here we go. So the 3-particle non-flow contamination. It's really, really hard to measure it from data. It's very difficult. We can't really do that now. So we use model input, okay? And this is the ratio that we defined. It's the 3-particle contribution divided by 2-particle contribution. The 2-particle contribution is really just the V2 non-flow. So this is the V2 non-flow, and we use hygiene and Pythia models. 2 reasons. One reason is that these models are QCD inspired. They describe reasonably well the jet fragmentation, string fragmentation, which are very relevant for 3-particle correlations. Second reason is very technical. Those models do not have flow, do not have V2 flow. So their entire 3-particle correlation is non-flow. So we can just calculate 3-particle cumulants and we get it. We can really do that for AMPT and all those. But these models are good in terms of the 3-particle correlations, like jet correlations. So I think this is very good, convenient for us. This is the 2-particle correlations from the models. We use hygiene, quenching on, quenching off, Pythia. And actually, we use 2 versions of radial flow. We put in radial flow into hygiene because radial flow is important. And that changes the correlations because you focus in the particles. by radial flow. And actually, the change is quite big for one versions of the blast wave modeling of the radial flow. A huge change in two-particle correlation. Also a huge change in the three-particle correlation. Okay, so two-particle correlation, three-particle correlation for event, sub-event, and that's the ratio. And the ratio is quite robust. Very weak centrality dependence, weak dependence on the models that we studied. And this is for event, this sub-event, you notice the magnitude is approximate effect of 2, and that's what I would expect. It's a simple acceptance effect, okay? And this factor of 2 makes sense. It's very good. We are continuing to investigate systematics because this is really a model input. So we need to be very careful about that. So with that, can I? Oh, okay, great. Okay, great. Oh, okay, great. Yeah. Yes. 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 Yeah, it worked. Very briefly on the systematic uncertainties, we've done extensive studies of the systematic uncertainties. I'm not going to talk about details, but just to say that we have systematic uncertainties in the data analysis by changing cuts and so forth. We have systematic uncertainties in the non-flow, V2 non-flow fit. And we have systematic uncertainties from the three-particle model input, and all together added in quadrature. All right, so now these are the FCME results. Okay, so many plots, so let me walk through. These are the measurement. 4 events, sub-events. This is the delta gamma over V2 scaled up by multiplicity, just to put them onto the same scale. Oh, 5 minutes, okay. And these are the measurements. These are the model input, the 3-particle over 2-particle contribution we call CSI. Okay, that's what you see already. The correction, the V2 non-flow correction is simply minus the non-flow fraction. The 3-particle correction is this divided by the data, okay? Here you have factor of 2 in the CSI. This is less than factor of 2 because we do know that the delta gamma over V2 is smaller in the 4 event than sub-events. We are absolutely sure about this. We are reasonably confident about this. This is the ratio. You can see that this is approximately 1 for sub-events, minus 1. So the correction is small, which is here. Okay, so this would be the green band with systematic uncertainty would be the non-flow correction. Okay, the difference is here. The breakpoints are just the original FCME observed with only flow removal, but not non-flow removal. The correction is small. The 4 event correction is relatively large. Okay, and we understand that just because of this. Okay. We are 100% sure about this. We are reasonably confident about this. So I think the relative thing is real. Okay. With that, I do want to just tell you that we did some closure test using hygiene. So basically, we take hygiene, we put in V2 into hygiene. So now the hygiene looks like more like data with V2. We treat that as data. We go through the entire procedure. We get the final FCME corrected for flow that we put in, and also non-flow. And that's consistent with 0. So that's good. That tells us that the procedure works. It checks out. Okay. So this is the final plot that slide that I have for you. This is the average FCME, final FCME after flow and non-flow correction. This is the only flow correction. This is now non-flow contamination removed. 4 events, sub-events. This is 20 to 50%. This is peripheral 50 to 80%, and this is the overall average over the entire measured centrality range from 20 to 80%. Okay, this is the FCME fraction. Significant in 4 events, about 30%. Weak centrality dependence, and as I said already, 4 event is larger than sub-event. Now, really to compare the CME signal itself in delta gamma. So this is a delta gamma CME, which is the FCME times the inclusive measurement. We know that the inclusive measurement is larger in sub-events. So this is now the delta gamma CME after flow and non-flow removal. And actually compare 4 event with sub-event for the 20 to 50%, they are compatible. They are actually within 1 sigma. But for the peripheral collision, we do seems to see some significant difference. Now, we are still thinking about it, still looking into it, but I should also say that it is possible that the CME has eta and or delta eta dependence. Okay, and one example would be what Gego talked about, the local CME fluctuations. But we are still looking into that. So with that, I will just summarize. So I think that flow-induced background is now well understood and under control, particularly by this comparison measurement with the 2 planes. And we have revisited the Gorda-Gorda collision data. The additional backgrounds from non-flow contaminations have been studied. I would say rather extensively, but we are continuing to improve or understand, particularly the model input. We decompose flow and non-flow in V2 by a fitting procedure. We obtained the 3-particle contamination from model through this ratio, particularly from hygiene and Pythia. And the Cassie ratio seems to have weak dependency on the models that we have studied, and seems to be robust against collective radial flow that we put in. By assuming these Cassie from models, we correct for the reaction plane independent 3-particle correlations in data, and we extracted FCME. Now, further scrutiny is still ongoing. For example, the Monte Carlo model closure tests is still underway. We did hygiene, but we need to understand more about the model and the model dependencies and so forth. I will leave it at that. Thank you very much for your attention.
All right, thank you very much, Fuqiang. So we have time for questions.
Thank you, Fuqiang. Could you show the previous slide, please?
Yeah.
So I wanted to ask, what is the statistical significance of the extracted fraction of CME? I mean, if I just look at this plot, naively, it would seem to be it's about 5 sigma, but since you warned me many times that I have to be very careful in interpreting experimental results, I just wanted to confirm this with you.
Yeah, I do know the number, but I feel that we're probably not, a number sounds too rigid and solid at this moment. So I would say it's, if this holds, it's rather significant.
No, but come on, I mean, can I just take the standard deviation and count how many?
Yeah, you can take the error bar, take the quadrature sum of the statistical and systematic uncertainties, and you can get that. Yeah.
And what do I get then?
For this number, I probably can just tell you that for these 20 to 50%, it's 3-point-some sigma, between 3 and 4,
right.
And for this is about 5.
Yeah.
For this is also about 3 for peripheral collisions. For the sub-events, it's it's smaller. Yes. Yeah. Yeah.
Thanks.
Yeah.
You know, it's firm, but not 100%. So, Aihong.
Yeah, Fuqiang. So, you know the strong magnetic field may polarize quarks. And then that effect will be rendered by your method as the CME also is non-CME origin. So I don't know how you plan to deal with it. And the reason I'm asking is I have this big worry that you seems has put a significant amount of time trying to beat down flow and non-flow. But as I see it, the magnitude of the uncertainty in our knowledge of the rho 0, 0, the plane-dependent rho 0, 0, could easily overshadow all of your non-flow estimate or flow estimate.
This is a physics question, yes. The spin alignment of, say, a low meson, for instance, if the spin alignment is really due to orbital angular momentum of the participants, this would be just like flow, and that's already moved. If the spin alignment is really, or there is a component of the spin alignment due to the magnetic field, then this is, you have the decay back-to-back emission from the rho along the magnetic field. I don't know how to distinguish that. So that would be included in the CME, FCME signal. I just don't know how experimental we can distinguish these two. So I think it's a physics interpretation.
All right, I think I have to cut the discussion, but there is the coffee break, so you can ask additional questions later. So let's thank Fuqiang and the speaker of the morning, and grab some coffee.